Assalamualaikum and hi, my name is Muhammad Walid bin Salih. In this presentation video, me and my teammates will present a little bit about Green's theorem. Let's see a simple closed smooth curve with orientation of counterclockwise that simply connected region R in the plane by assuming vector field F with the component of F and G, where F and G have continuous first partial derivative in region R. Then the integral of closed curve C vector F dot d vector R, or in its differential form, equals to double integral over region R partial derivative G respect to x minus partial derivative F respect to y dA. Remarks that the dA can be dx dy or dy dx. Sometimes in another book, F will referred as capital P and G referred as capital Q. Based on the equation, we can see that the Green's theorem actually relate line integral, which is single integral around a simple curve C, to a double integral over a plane region R that bounded by curve C.
Morning everyone, my name is Rinesh Ravindran, and now I'll be continuing on why is it important for us to use Green's theorem. So basically, it's much easier for us to compute the line integrals around a simple closed curve C. But the condition for that is we can only apply this theorem for the curve that is in 2 dimensions. So as a detailed explanation, line integrals are typically harder and more complicated to be calculated than ordinary integrals, since there are extra equations and workings. So through the Green theorem, a more convenient way is presented to calculate them in closed curves. For example, instead of using the first equation to compute line integrals, as you can see, it has more equations and formulas to be used. We can just apply Green theorem, which calculates them easily and conveniently. Also, with the help of Green's theorem, it is possible to find the areas of closed curves. The line integral defined by Green's theorem gives the area of the closed curve. Therefore, some examples of the area formula is as shown below. So 3 of those can be used to calculate the area of closed curves. So now I'll be talking on requirement and regularity condition before applying the Green's theorem. Number 1, the curve must be a simple curve, no self-intersection. Number 2, the curve must be a closed curve, both endpoints meet each other. And the curve must be a smooth curve. And lastly, the curve is in counterclockwise oriented, which gives us the positive sign. For clockwise also, we can compute it with this theorem, but we need to switch the sign. So from positive, we need to make it negative. That's all from me.
Good morning, madam and viewers. My name is Vignesh. Now I'm going to explain about the example 1, which can be solved using the Green's theorem. So the question is, evaluate the line integral where C is the circle x squared plus y squared equal to 4 transferred counterclockwise. So our first step is to sketch the diagram. So I use the algebra to sketch the diagram. So this is a region R with a radius of 2. So our next step is rewrite this line integral as a double integral over the region R. So the x component of vector field F is equal to little f and the y component is equal to g. So the partial derivative of g respect to x would be 1 minus the partial derivative of f respect to y would be negative 1. So here we just going to f double integral over the region to dA, which is just 2 times the area of this region. So the area of this region is pi r square, where r is 2. So we will get which is equal to 8 pi. To confirm the answer, we can try another method, which is by converting this equation to a polar form. And remember, when we do that, we have an extra factor r, then dr d theta. For r would be 0 to 2, while for theta is 0 to 2 pi. Since we are looking for the area of entire circle. And okay, we know that the answer should be 8 pi. So, but let's go and just verify it using a longer method. So we have 2 times r squared over 2, which would give us r squared. This would be just be a 4 minus 0. So we have an integral from 0 to 2 pi of d for d theta. So we have for d theta, then substitute the 2 pi and 0, and you can see here that we have 8 pi minus 0, or which equals to 8 pi. So the result is same regardless of whether we take the shortcut by just multiplying 2 times the area of region, or we convert to polar form and evaluate the longer way. That's all from me. Thank you.
So I'm going to show the second example of green theorem. So the question will be to evaluate the integral of square of 2x square y dx plus y x dy, where c is the square with a given point of vertices 0, 0 to 0, 0 to and 2, 2. So we draw a square and plot the given point, and we show the flow of the square, which is counterclockwise from 0, 0 to 0 to 2 to 0, 2 and backward to 0, 0. So based on the formula is p dx plus q dy, where we need to differentiate q in respect of x when we need to differentiate p in respect of y. So the both result we will need to minus p from the result of q s. So to x square y is p, y s is q. So we differentiate to x square y in terms of y. So we will get 2x squared, and we will differentiate yx in terms of x, we will get y. So based on Green theorem, we need to do the formula of q minus p. So it will be y minus 2x squared. So the boundary, the upper and lower boundary is 0 to 2, because the x-axis is from 0 to 2 and the y-axis is from 0 to 2. So we'll need to do the integral, and first we will integrate in respect of x. So the answer will be 2y minus 16 over 3. So the last step is we will integrate in respect of y. So the answer will be 2 square minus 16 times 2 over 3. So the answer will be negative 6.67. That's all from me for the example 2.